I think I'll start the presentation, and we've got the fruit boy running around. If anyone wants any fruit, is that what it's for? Okay, good. So you got your fruit. So if I'm no good, you just throw it at me. Apparently. So my name's Jesse Clarke. I'm the building science manager for Clima for Australia and New Zealand, and I guess as a bit of a background, I used to work in my previous role for a very large building products company based in Australia that manufactures everything from plasterboard, insulation, glass, fibre cement, roof tiles, and everything else you can think of. So some of the stuff I got in here is about material properties and how we can progress the use of WUFI forward in the mass market, get everyone using it to try and increase the healthiness or the healthy outcomes and the durability of our building structures. So thank you to Hartwig for the introduction. And yeah, we'll kick off. So basically, in Australia, just to give you an outline of what's happening there, we've got this scenario occurring where in 2014, there was all this stuff going around about condensation in buildings, and the Australian Building Codes Board released this handbook, which was condensation in buildings guide or handbook to condensation in buildings. And in Tasmania, there's big issues with moisture in buildings. So in that same year, 2014, there was a condensation in buildings Tasmania Building Designers Guide that was released. And then in 2016, the ABCB did a big survey of the whole industry out to all practitioners and everyone involved in the industry. They got the biggest response they've ever had from any survey they put out. And they basically found from that 40% of all Class 1 and Class 2 buildings, so this is freestanding housing and multi-unit, multi-residential apartments, have condensation problems. And basically, they said, yeah, it's a complex problem and it needs a holistic approach to the problem. So as you see from all the research that Fraunhofer has been undertaking for the last 40 years, this is all about integration of the building envelope with the mechanical systems and the climate in which you're building the building. So that is essentially a holistic approach can help us solve this problem. 2018, just last month, there was this report that was released. It was a Commonwealth inquiry into biotoxin-related illness in Australia. So the real problem is not necessarily moisture or condensation in buildings. Condensation itself is not going to kill anyone. It's the side effects of moisture in our structures that we need to worry about. And there's discussion rolling on now. And as you can see from the progression happening here, that there's now that link being made between wet buildings, soggy buildings, and health outcomes with mould. So we've got these moisture problems occurring in Australia. It's the same thing that happened in New Zealand. The places we're seeing the moisture problems in Australia worst are in Tasmania, Victoria, Canberra, all the coldest regions. But Tasmania and Victoria are essentially on the same latitude as New Zealand, roughly. So it's similar climates, and we're seeing those same problems that New Zealand got from the New Zealand leaky building crisis. And it's just interesting following that progress. And also in 2015, the Building Codes Board introduced new requirements for weatherproofing into the building code. So we have full-scale facade testing for the facades, which has the facade test with the windows integrated and all the features in there to test all the connection points and everything. The interesting thing is how much you find out when you do those large-scale weather tests, and finding out where the water goes is amazing. So very important process. So what I was going to talk about is mass market adoption of WUFI. So how do we get there? So there's certain things that need to be put in place. And part of that is, I guess, relieving the fear of practitioners. And part of that is standardization. So standardizing the process by which you can calculate WUFI or do WUFI analysis. And then we've got to look at the inputs and outputs to WUFI. So weather data that goes into WUFI, material properties that go into WUFI, and then the internal conditions, so what's happening inside those buildings, and making sure that everyone's comfortable in using WUFI and that they're comfortable in the results that come out of WUFI, that they can actually give industry guidance on based on those simulations. So I guess what becomes standard is what is generally agreed between practitioners. And if everyone's doing the same thing, then if it's industry standard, then people are more likely to use the software. So without that standardization process, we have a problem. But in Australia, I'm the chairman of the AERA Special Technical Group. So AERA is the Australian Institute of Refrigeration and Heating. And the Special Technical Group for Building Envelope Physics is looking at adopting an ASHRAE standard. The ASHRAE, is everyone familiar with ASHRAE? The American Society of Heating, Refrigeration and Air Conditioning Engineers developed a standard which basically looks at, it's a general standard. You can use any hydrothermal simulation software package. There are a few out there, and it guides those inputs and outputs. So essentially, we're going to adopt that into Australia. We're going to localize it. By localize it, I mean take out all the BTUs and feet and all those units that we don't understand. Take out all that stuff and just leave the DSI units, and utilize that as a standard to guide the practitioners. So once we've got that standardization in place, I think there's going to be some sort of the practitioners will be more confident in using the software. The other big issue we've got is a chicken or the egg problem. It's if we don't have the users in place and people aren't using the software, the product manufacturers aren't likely to come to the table and invest the money to measure product data. So how do we get this? How do we break that cycle? How do we get enough users so the manufacturers go, oh, there's a market here, I can get some marketing leverage. I'm going to test my data and I'm going to put it in the database. So that's what we're looking to achieve. So in terms of the material properties, there's some fundamental properties that go into WUFI that we need to understand better. But the idea is, or one of the ideas I had is to create a generic database of material properties. But that doesn't necessarily have to be fully tested to the nth degree. There's 600 materials in the international WUFI database, so from all around the world. And when you know materials well, you know that glass wool is basically 99% air or more. So it doesn't vary that much whether it's a piece of glass wool from America, Europe, or Australia, or New Zealand. And once you know that all the technology is licensed from either American or European countries and then manufactured in Australia or New Zealand, then you know that essentially they're the same products. Maybe a little bit of quality difference, but apart from that, same products. And then you know, once you go to the fibre cement products, if you know your products again, well, there's about 6 recipes internationally. You just got to know which one's which. And some key measurements on the product moisture content. And then if I go into another chamber at 50% humidity, I get another measurement. It'll have more moisture content in that porous material. So measuring these sorption curves, and you progressively increase the humidity in the chamber or in different chambers and put the materials in there, you can measure that whole sorption curve up to basically 100% humidity. And if we get just general basic measurements for some materials, not necessarily a full set, and then correlate that to existing materials that already exist, this is a quicker pathway I see to be able to get a generic material list to give the practitioners guidance. So there's all sorts of properties that we do know about our products in Australia and New Zealand, like thermal conductivity. We know densities, porosity probably not, but matching those densities and fundamental key measurement points at certain properties, we can essentially estimate what they are. Yeah, so that's the material side is very important. So we are seeing a lot of problems that you guys have, or probably see a lot in New Zealand, which is this condensation on windows and mold growth. But in Australia, there's stuff happening. Before going back a step, the building code for 2019, the building code board is looking at putting new requirements into the building code. Sorry, too far away from the mic. Looking at having new requirements in the building code, and it's going to have a dual pathway. So there's a verification method or performance-based method to get through the code for condensation or moisture management, and there's a DTS, a deemed to satisfy method, which is basically saying in all the coldest regions of Australia, climate zone 6, 7 and 8, which is essentially Victoria, Tasmania, Canberra, all the cold places, you have to have vapor permeable membranes on the outside of your insulation layers. So this is nothing new to the New Zealand market because we've been using vapor permeable membranes for donkey's years. But Australia is a bit slow and we're just catching up now in that respect. But we've got massive amounts of aluminium foils used on buildings everywhere in Australia, and that is essentially suffocating buildings. The other issue we've got, which was talked about at the ERA Building Physics Forum last week at the University of Wollongong, was in commercial multi-res, we have people put in metal backpans or metal drainage planes behind the cladding materials, and this is to meet new fire requirements after the Grenfell Tower and all these issues with buildings going up in flames. So the builders, and I guess it's driven by the builders and poorly educated engineers, that the metal backpan is non-combustible material. When you put it in the furnace, it doesn't go up in flames, so therefore it's okay to use. So what you end up doing is having metal backpans on the outside of the insulation layers that trap all the moisture. So everyone in the room is probably going, yeah, that's a dumb idea. Yeah, I know, but it's getting done. And I've fought these battles just on the phone with builders, and essentially I say, I don't believe any of it, I'm going ahead anyway. So, okay, all right, I'll talk to you in 5 years' time. So we've got that problem emerging, and that's what this is all about. This is all about trying to combat that and get healthier, drier buildings. And this verification process that you can see up here is essentially, I've got some, looking at mitigating the risks of moisture accumulation in the building envelope or condensation. And the risks are essentially biotoxin, corrosion, and timber rot. So it's structural, it's health and structural issues. And you can do an assessment, you can do a modeling. So use computer modeling to assess whether you're going to get damage and you're going to get high humidity and moisture accumulation. And that would be based on indoor conditions inside the building, would be based on the weather, where you build in the building outside, and the materials. So I touched on that, I was talking about material properties. And you need to make sure that interior to the primary water control layer, so if that's a metal backpan, you're not going to get any moisture accumulating. So metal backpan is probably a bad idea, and you need to move to more vapor permeable sheathing materials in that case. So WUFI is very good for analysing cases and going option A against option B. And in this particular scenario, this was me looking at a precast concrete panel, which is often used in multi-res apartments, and different ways of insulating it with and without a vapor barrier in that system. Because a lot of time we just have foil face blanket plonked straight up on the inside of the concrete panels. And in this particular case, what you see is when you have the vapor barrier in there, you create high humidity behind that vapor barrier. So the moisture stored in this masonry, in the concrete, you've got about 100 kilograms per meter cubed, and that moisture can go outwards or inwards, and it creates high humidity behind the vapor barrier. Or if there is no vapor barrier, at times of the year you get elevated humidity on the interior surface of the plasterboard. So then that might become an issue for mold growth on the plasterboard. So you can look at all these different options using hydrothermal simulation and design systems in the best manner to get the best outcome. So how do we get to this mass market adoption? And I think in terms of looking forward towards the light at the end of the tunnel, we need to go to standardization, which I mentioned. We need the weather data, we need good weather data. New Zealand already has it. We need material data, which I touched on, internal conditions. We need to agree on that, and collaboration. So we need to talk and share knowledge and be open about all this information and all these I guess all these aspects up on the screen there. So I mentioned the chicken or egg approach or problem, which is, do we have practitioners and a whole bunch of practitioners before the building product manufacturers get on board, or do the building product manufacturers come on board and then everyone has confidence and then we build it's probably going to be getting the practitioners on board first. So the problem is, yeah, there's fear out in industry. Standardization does remove some risk. In that everyone's doing the same thing. So if you're doing standard practice, then hey, that's standard. So don't blame me if it goes wrong. Not necessarily the best defense, but the idea is to increase that knowledge level so you're confident in what you're doing will work. And the issue I've seen, I've sat on a lot of standards committees in Australia, And standard practice is generally code compliance, because code compliance is whatever is the standard practice, because everyone reverts to lowest common denominator. And the standards aren't allowed to drive better practice if it's a code reference document. So therefore you can't use the standards to increase practice, or you can't use code reference standards to increase practice. You need new standards, better standards. You need high performance standards that guide the industry in the right direction. Otherwise we'll just be incrementally changing everything and get nowhere. And who carries the risk if it's a legal requirement but it doesn't work? Well, that's, I guess, the big issue. So what happens if you do design these things and they don't work? And that's, I guess, what drives the fear. And new things are generally, people are very scared of new stuff. So that's the standard. That's the ASHRAE 160 standard that we're looking at adopting. And that will guide the use of hygrothermal simulation. So what ASHRAE 160 does, it does all those things. So it enables us to assess that durability and long-term moisture effects issues. We have a new standard that was released in Australia. I don't know if everyone's familiar with that, but it's around membranes and membrane properties. So the part 1 is Australia and New Zealand standard, 4200 part 1. So it has 4 classifications for membranes, class 1, 2, 3 and 4. Class 1 and 2 are vapor barriers, class 3 and 4 are considered vapor permeable. That's all just, that's just words, right? So you've got these new categories, but the real thing is, what is the number? What is the vapor resistance and vapor permeance that you need on those membranes to work in a particular construction system, in a particular climate, for a particular building use? And what we need to get to is a point where people are actually specifying the meganewton seconds per gram vapor resistance or the vapor permeance of the membrane that they're specifying. And that's what this is all about. So we're looking at adopting that ASHRAE standard as a industry guide, an NERA industry guide, and hopefully that will happen sooner rather than later. So as I said, New Zealand's pretty good on the weather data. In Australia, we're struggling a bit. We don't have any hygrothermal data yet. We have had discussions and people are interested. So CSRO, we were talking to yesterday, and they're like, yep, we think we can do that. We can develop weather files that will have rain data in there. Rain is critical because we need to be able to analyze what happens when you get wet, soggy materials or rain into the construction systems. So in Australia, you go, well, it's not that cold, so maybe we don't have any vapor diffusion problems. But what we do have is places where it rains, sometimes not at all, but sometimes it rains a lot. And that is in the tropics and all the coastal regions. That's where it dumps all the rain. That's where the people live. People live where it rains. And I guess that's a historical thing because the Europeans didn't want to live in the middle of the desert. And temperature and humidity, we've got this problem. Hartwig said he learned that there's just as many or more problems with humidity on the external climate, as in the tropics, as there are in the cool regions. And the problem we have in Australia and New Zealand is that you get this reverse vapor drive. One season it's going one way, the other season it's going the other way. And we need to design our buildings to be able to handle that. So mixed climates, to me, well, what I've found out is mixed climates are actually harder to design for than permanently freezing cold or permanently hot and humid, because you only got one direction that you care about. So that's when it gets tricky. And material properties I touched on. So WUFI, everyone's used WUFI. Everyone familiar with WUFI? Yes, no? Experts, some experts? Yeah. So just put your hand up if you have used WUFI. Okay, so there's quite a few people that haven't. We might have to do a demo, Matt. But WUFI has material properties that go above and beyond normal standards. Normal standards are generally just say, I want to measure at this temperature, at this humidity or whatever it might be, and you measure 1 point, and then that's what all the manufacturers compete on, this one test point data. WUFI says, well, okay, or the way WUFI works, it needs a whole spectrum of data. It needs to know what happens across the whole range of temperature and humidity. And that's all these temperature and humidity variable functions for different parameters in WUFI. So the water content of the material is actually dependent on relative humidity. That's called the sorption curve. We have water content versus liquid transport through the capillaries in the structure. We have relative humidity versus water vapor diffusion. So some products actually change their vapor diffusion properties based on the average relative humidity across those products. So 1 point is not good enough. And temperature dependent thermal conductivities. So all products change their thermal conductivity based on temperature. They also change their conductivity based on how much moisture is in those materials, particularly with porous products. So when you start talking about concrete and masonry or aerated concrete in particular, if it gets wet, it loses its K value, or its thermal conductivity goes right up through the roof. So we need to understand what's happening in those structures. So we need a lot more product data to be able to do hygrothermal simulations. So maybe this is a bit complex, maybe not. What's critical to the sorption curves and understanding the amount of moisture in products at certain relative humidities is what happens when you get to the very high end of the spectrum. So when you start going up to 100% humidity or close to, then you get this really steep curve in that the products can get really, really soggy. They can hold a lot of moisture when you get up to really high humidities. And that can be critical, maybe not, depending on what sort of material and where it's used in the structure. So what happens in porous materials, porous structures, is essentially you have water molecules within the structure. So this is what I was describing when my PowerPoint crashed. At low humidities, you have a certain amount of water molecules that start to line all the pores in the structure. And as you move to higher humidities adjacent those materials, they collect more water molecules in all the pores. And that increases as you go further and further up the humidity spectrum, and eventually you start getting layers and layers of water molecules until they essentially get completely filled up at maximum saturation. So we need this data. We need to look at how we get all that data out for different materials. That is not actually that hard to measure. So when you're talking about what the moisture content of materials is at different humidities, this, a simple box like this, or even big chambers, humidity chambers are used in all sorts of industries for all sorts of things. But if you've got a humidity chamber at a certain, held at a certain humidity, you can just throw products in there and measure the moisture content on scales, essentially. So it's not that hard to do to get a sorption curve, or at least part of the sorption curve. And an example of this is here. This is a piece of fibre cement. It's a RAB board, an external sheathing board, fibre cement from Australia, and it's got 4 data points. So I say, great, I've got 4 data points at 20, 50, 60, 90% humidity. And then I've got 600 WUFI materials, and I say, well, all the fibre cement, or a selection of fibre cement materials out of the WUFI database are all overlaid there. You say, well, which one does it look like? Well, it's one of those two. So I pick them up and say, okay, now we've got a correlation. I don't necessarily need the full data set. I just need some data to be able to estimate the products. I think that's a quicker pathway to getting some decent product data that is reliable, or that is useful in Australia and New Zealand context, and working together to get that sort of data, collect the information, and work together to develop a generic material database while we progressively get product manufacturers to get specific materials into the database. Vapor diffusion is a really easy test to do as well. Essentially, it's just a cup. You get these little plastic cups and you put a sample of the material on it, and you measure weight gain or weight loss. And it's a little plastic cup, and you put in that cup a dry cup test. Is you put a desiccant, like those little satchels that keep your food, your noodles dry. You put that into the cup. In this case, calcium chloride, you put it into the cup. That holds the cup when you put the sample on at basically zero humidity. And the humidity chamber that it's sitting in forces water into the material, and then you get a weight gain of the sample over time. So it's really simple. The reason I'm telling you this is because you can have these discussions with anyone you come in contact with when you're out in the market. Product manufacturers, you can say, well, actually, it's not that hard to measure. We need this data, and this is how it's done generally. And then there's a wind speed that you need to correct for, but let's not get into the detail. So then you go to wet cup tests, and wet cup test is essentially you put a solution in the cup, which changes the humidity. So you put the sample on top, and it sets a certain humidity in the cup. And then when you've got the climate conditions in the chamber set at 23 degrees and 50% humidity, if it's humid in the cup, it actually drives water vapor out of the cup, and the sample will lose weight over time. So you've got a weight of water, and you've got the driving force, which is that vapor pressure created by the temperature and humidity on either side. And this is how you measure diffusion properties of materials, not just at one point, but across the whole spectrum, and that's what we need. So basically they give you different answers, potentially different answers depending on the product. So materials that are measured at different humidity ranges can have this variable vapor diffusion function, particularly if you're looking at porous materials, and things like timber can have different vapor diffusion properties at different humidities. So we need to, when we start looking at data and you're picking up vapor diffusion tests from all over the world, they might have different test conditions. So we need to understand what test conditions they're tested at. And then we're looking at properties of materials for suction curves. So how much moisture is sucked up through materials. You sit samples in wet in basically a soggy bucket, let it suck up through the capillaries, and then use a NMR scanner to work out how much moisture has been sucked into those pores. The other thing, which I mentioned, is the internal conditions. This is interesting because this was calculated for Australian climates, and this was presented by Hartwig at the Building Physics Forum last week in the University of Wollongong. And the ASHRAE 160 basically looks at the internal conditions, which are calculated from an air leakage rate of the building, how much volume of the space. So a small building or a small apartment that has lots of people in it will obviously increase the humidity in the apartment. So the ASHRAE 160 balances these three key things together. And the interesting thing is, when you use those algorithms for those assumptions, they're listed there, in all the climates around Australia, you get different internal humidity conditions. And that makes sense, because in a dry climate like Alice Springs in the middle of the desert, when you get air mixing and with the indoor air, you get a lower humidity. And that's how it's calculated through ASHRAE 160. And the interesting thing that Hartwig learned was that we actually do have very high humidities in our buildings in Australia. And in Germany, apparently, 60% humidity, 65% humidity is considered high. Yeah, so that's a very high. So we are actually getting humidity in our building, and this was confirmed by all the engineers at the forum. They said, yeah, that's true. I've measured 80, 90% humidity in our buildings. So all that water vapor pushes through the building envelope. So there is a sensitivity to the internal conditions you choose. But with the simulation, the beautiful thing about that is you can play with sensitivity of all these parameters and use your expert judgment to decide whether the system is resilient under certain conditions. So knowledge sharing, collaboration, very important, and that's why we're here. So that was taken by some paparazzi at lunchtime. So that's why we're here, and let's discuss that. Let's collaborate, let's share knowledge, and work out how to solve this problem and get WUFI and hydrothermal simulation mainstream so we can build healthier, drier buildings. And we've got to stop doing this and do this. So how do we get the ball rolling? Let's discuss.